the active section, and the additional value k. The problem statement got cut off, so let me narrate what's clearly given and flag the gap. Here's the narration based on the complete part of the problem. You're given a binary string of length n, where each character is either a 1, meaning that section is active, or a 0, meaning it's inactive. Your goal is to make as many sections active as possible. To do this, you're allowed to make at most one trade, which happens in 2 steps. First, you take a solid run of ones that has zeros on both sides, and turn that entire run into zeros, and turn that entire run into zeros. That has ones on both sides, and turn that entire run into ones. Heads up, your goal is to make as many sections active as possible. You're given a length put and the on plug the gap. Beginner level, don't let the word hard scare you. This entire problem comes down to spotting one little shape. A group of ones with zeros sitting right next to it on the left and the right. Think of it like a sandwich, with the ones as the filling and the zeros as the bread. When you remove that filling, the bread on both sides joins together into one bigger piece. By the end of this video, you'll spot that little sandwich in seconds. Take a breath, we'll go slow. First, let me define one thing. A string is just a line of characters. Here it's only zeros and ones. A range query means someone asks a question about one chosen slice of that string, not the whole thing. These questions pop up everywhere in real software. Text editors rearranging your lines, tools that scan DNA, and systems that pack data into bits. Big companies like asking this kind of question because it looks scary but hides a friendly little idea. Learn the idea once and you'll reuse it for here's slice a friendly little idea. Learn the idea once and you'll reuse it for years. Here's the one move you get. First, take a lonely group of ones that has zeros on both sides and turn those ones into zeros. Then take a group of zeros that has ones on both sides and turn those zeros into ones. After the move, we count how many ones exist in the whole string, not just in the part we touched. That sounds abstract, so let's watch it happen on a tiny example next. Let's walk through this one character at a time. Our string is 0, 0, Z that. See that single one sitting almost in the middle? Erase it, turn it into a 0. Now the whole string is 0, 0, 0, 0, 0, zeros with ones pressing in from the edges. Fill all of them in and you get 5 ones in a row. Notice this, that one little one we deleted was the key that unlocked the zeros on both of its sides. Nice work if you followed that. Let me define 3 words before we go further, one at a time. A run is simply a streak of the same character in a row, like a row of dominoes that all match. Precompute means we do some counting once at the very start so that later on our questions are quick to answer. And as sparse tables is just a cheat sheet we build ahead of time, you point at any range and it instantly tells you the biggest value inside. That's all these words mean, everyday ideas with fancy names. Here's the heart of it. Every good move is a run of ones with zeros on both sides. When you delete those ones and fill in, you gain the zeros on the left plus the zeros on the right as brand new ones. So the whole puzzle boils down to one friendly question. Out of all the sandwiches in our slice, which one has the most bread, meaning the most zeros around it? Let's give this shape a name so it's easy to remember. The 0, 1, 0. Step 1. We walk through the string and break it into runs, those streaks of the same character we defined earlier. For each run, we jot down its character and where it starts and ends. Here's a comforting fact. The total number of ones never changes. When we make our move, we only rearrange them. So the final answer is always that, total, plus whatever extra we can gain. We count the total just once, and then set it aside. Step 2 is our pre-compute, the counting we do up front. We look for every run of ones that has a run of zeros on both sides, a real 0, 1, 0 sandwich. For each one, we write down where its edges are and how much we gain, the left zeros plus the right zeros. Doing this work now means that later when questions come in, answering them is cheap. We pay once instead of paying over and over. Now it's your turn and there's no rush. Pause the video and try this yourself. The string is 1, 0, 0, 0 and you're allowed to work on the whole thing. There are already 2 ones in it. Find the best 0, 1, 0 sandwich, add its gain to those 2 and see what number you land on. Give it a real try, then press play and we'll check it together. Let's check it together. Look at the one sitting at position 4. It has 3 zeros hugging it on the left and 2 zeros on the right. So its gain is 3 plus 2, which is 5. Now add the 2 ones that were already there and you get 7. That's it. If you got 7, great job. If not, no worries at all. Trace it once more slowly and you'll see it. Same little pattern doing all the heavy lifting. Step 3 handles each question, which asks about one chosen slice of the string. We quickly find which sandwiches fit inside that slice. The 2 sandwiches at the far ends might stick out past the slice's edges, so their zeros get trimmed to fit. We adjust those 2 by hand. Every sandwich in the middle sits fully inside, so it keeps its full gain, and our cheat sheet, the sparse table, hands us the biggest one in an instant. Slow to build, lightning to ask. Here's a lovely little insight. Only the leftmost and rightmost sandwiches can have their zeros cut off by the edge of a chosen slice. Every sandwich in between is safely tucked inside, so the gain we measured earlier for it is still exactly right. That's the whole reason two quick hand checks, one for each end, plus one instant lookup for the middle, is enough to answer any question. Two special cases, and you're done. There's an obvious, simple approach too, and honestly, it's a great starting point. For each question, you rebuild the little slice, break it into runs, and scan through looking for the best sandwich. It's easy to understand, and I genuinely write this version first to double check my faster code. It works perfectly fine, right up until the input gets really big. Then it gets slow. Let's see how slow. Quick note on the shorthand, and just means how long the string is, and Q means how many questions we get asked. The simple way does about n steps for every single question. So a string of 100,000 characters with 100,000 questions means 10 billion steps, which is far too slow. The fast way does its upfront work, then answers each question almost instantly. Way fewer steps, and it finishes with room to spare. Let's gently cover the tricky situations. If there's no 010 sandwich at all, then our gain is just 0, and we simply return the total number of ones, nothing to trade, and that's okay. If the chosen slice cuts right through a run of ones, that run no longer has clean zeros around it, so it stops counting exactly as we want. And if the slice is tiny with nothing to work with, our simple check spots that an empty case and handles it safely, no surprises. Let's recap the whole thing gently. Remember that little sandwich? Find the best 010. Add its gain to the total number of ones, and you have your answer. Do the counting up front, trim only the two edges, and let the cheat sheet handle the middle. That's the entire hard problem. You did it. Tomorrow, this same run and lookup idea unlocks a trickier puzzle, same time, and you're more than ready for it. Some things in tech really are hard. This one wasn't, and you're more than ready for it. Some things in tech really are hard. Intermediate level, one tiny pattern cracks this entire hard problem. It's a block of ones hugged by zeros on both sides. Delete that middle, and its two zero neighbors fuse into one fillable gap. By the end, you'll spot this sandwich in seconds. Range queries over strings show up everywhere. Text editors, reflowing lines, genome scanners, storage systems, packing bits. Companies love this exact flavor because it hides an easy idea under a hard costume. Learn the trick once, reuse it forever. You get one trade, turn an isolated island of ones into zeros, then turn an isolated pool of zeros into ones. We count active ones across the entire string afterward, not just the window. Watch what happens on a tiny example next. Take 00010, erase that lonely one, and the whole strip is zeros surrounded by ones. Fill in by ones. Notice the middle one we deleted was the key that unlocked both zero gaps. 3 quick words, each an everyday thing. A run is just a streak of the same character, like a row of matching dominoes. Prefix means we tally everything up once at the start, so later lookups cost nothing. And a sparse table is a pre-filled cheat card that names the biggest value in any range instantly. Here's the trick. Every valid trade is a one run flanked by zeros. Deleting the ones and filling gives you left zeros plus right zeros. New active sections. So the whole problem is, over the window, which sandwich has the most bread? Name it the 01. 0. First we slice the string into runs, remembering each one's character and its start and end index. The total number of ones never changes across a trade, so the answer is always the total plus whatever gain we can squeeze. We compute total once and forget about it. We list every candidate one run that has a 0 run on both sides. For each we store its edges and its full gain. Left zeros plus right zeros. This is the pre-work that makes each query cheap. We pay once, not per query. Pause the video. The string is 1000100 and you can trade on the whole thing. Two ones already exist. Find the best 010 sandwich and add its gain. What number do you get? The one at index 4 is hugged by 3 zeros left and 2 zeros right. Gain of 5. Add the two existing ones and you get 7. There's the pattern doing all the work. Clean. For each query, we binary search which sandwiches fit inside the window. The two-edged sandwiches might have their zero gaps chopped by the window boundary, so we clip those by hand. Everything in the middle keeps its full gain, and the sparse table hands us the biggest one instantly. Here's the only the leftmost and rightmost sandwiches can have a zero gap sliced by the window edge. Every sandwich in between sits fully inside, so its pre-computed gain is exact. That's why 2 handchecks plus 1 range max covers every query. The obvious approach for each query, you on the boundary ones, split into runs, and scan for the best sandwich. It's clean, and I honestly reach for this first to check my fast code. It works fine, until the input gets big. Brute force is big O of n per query, so with 100,000 queries and 100,000 string, that's 10 billion operations. It times out. The sparse table version builds in n log n and answers each query in log n. My honest opinion, sparse tables are underrated. They're simpler than segment trees for pure max. If no 0, 1, 0 exists, gain is 0 and we just return the total ones. That's the no valid trade cases. When the window slices through a 1 run, it merges with the boundary 1 and stops qualifying. Exactly like the augmented one's intent. The I0 greater than I1 check catches empty windows safely. Remember the sandwich that broke brute force. Now you see, it was never hard. One pattern, pre-compute the gains, clip 2 edges, done. Tomorrow, this same run, plus range max trick cracks a much nastier interval problem, same time. Some things in tech are genuinely hard. This is not one of them, subscribe. AK advanced level, you already know the core. An isolated one run flanked by zeros, deleted. The 2 0 gaps fuse. The whole game is answer equals total ones, plus the best mergeable gap under range constraints. We're here for the boundary clipping and the query structure, not the reveal. The interview twist is almost always the range constraint bolted onto a trivial global answer. That's the tell to reach for run decomposition plus a static range structure. If they add updates, you're into segment tree or skirt decomposition territory instead. Keep that fork in mind. One trade and the invariant that matters, total ones is conserved. Erasing a one run, then flooding cost and refunds the same ones, so every trade's net effect is purely the zero gap merge. That's why we optimize gain in isolation and never recount ones per query. 0, 0, 0, 1, delete the interior 1. The strip is now all zeros bounded by ones on both ends, flugged to un11 1 when. The deleted one is what makes both neighboring gaps fillable simultaneously. That adjacency is the entire constraint on which gaps you are allowed to claim. Runs, prefix, precompute, sparse table, you know all three. The only design choice worth defending, sparse table over segment tree because gains are static and max is idempotent. So or even queries with no lazy propagation. If updates were on the table, the pick flips. Each candidate's gain is left, 0 count plus right 0 count of the flanking runs. Reduce the problem to over 1 runs whose sandwich fits the window, maximize that sum. The subtlety is fits the 1 run must be strictly interior to the query, which is exactly what the binary search boundaries enforce. Standard single pass run split storing, char and inclusive endpoints. Total ones is a one-shot count since it's invariant. Note the endpoints are absolute indices. That's deliberate because query clipping compares them directly against LNR with no offset math. Candidates are emitted in index order, so their A values and B values are already sorted. That's what lets the query bisect directly without a separate sort. Each tuple carries the one run edges A, B and the outer zero edges C, D, so clipping later needs no rederivation. Browse and one answer, full range query. Two ones exist. Best sandwich is the interior one, but confirm for yourself that neither gap gets clipped here since the window is the whole string. What's the answer? And which candidate index wins? Index 4, 1, 3 zeros left, 2 right, gain 5 plus 2 existing ones equals 7. The leading and trailing ones at 0 and 6 disqualify their neighbors as candidates. Only the interior one has zeros on both sides. That asymmetry is worth noticing. Bisect on L plus 1 and R1 selects candidates strictly interior. Only I0 and I1 can have a gap truncated by the window. So we recompute those two with clamps C and D. Everything strictly between is untouched and served by the sparse table. Watch the off by ones, L plus 1, R1 and the minus 1 on bisect right. The correctness hinge, any candidate strictly between easier and I1 has both flanking 0 runs fully inside L. RA, so its pre-computed gain is exact. Only the extreme 2 can straddle a boundary. That reduces per query work to 2 clamped evaluations plus 1 idempotent range. Max. No more special cases exist. The ON per query brute is worth keeping as an oracle for randomized differential testing. Augment with boundary ones, rerun the scan, compare. Cheap insurance against the off by 1 bulbs the fast path is riddled with. Then throw it at scale and watch it die. ONQ is 10 billion at 1 at 5 each. TLE, sparse table gives ON log min, build, log min query. Follow up they'll ask, what if the string mutates between queries? Sparse table is dead. You switch to a segment tree over candidate gains, log and update, and rederive candidates around the edit. Be ready for that pivot. empty candidate set, I0 greater than I1, return total. That also covers single char and gap free windows. The nasty one, a window slicing through a one run. Because bisect uses L plus 1 and R1, a candidate whose one run touches the boundary is excluded, matching the augmented one semantics exactly. Test windows landing mid one run specifically. That's where naive versions leak. Run decompose, precompute gains, bisect the interior, clip two ends, range max. The whole pattern. Same skeleton generalizes, static candidate metric plus sparse stable range. Max solves a family of interval problems. Next up, we apply it to a genuinely harder one where the candidates overlap. Subscribe. Take this string 001, 1000. If you can slide 10 run over, how long can the ones get? Pause and guess. Think about that 010 sandwich we drew earlier. You get 5. Sliding 10 run lets the 2-1 blocks touch and the leftover zeros pile up outside. We chop into runs and check neighbors once. What's the time complexity here? Pause and pick one. Remember, we never look back once a run is measured. It's linear O of n. We touch every character a single time while grouping the runs, no nested scans.